subtopic, mass defect and nuclear energy. All right, first thing, what is a mass defect? Say we take any example of radioactive emissions, okay? Just pick a random one, okay? X21292 break down to become whatever the atom Y20890 plus alpha. Okay, let's just take one alpha emission. This equation, you should notice that it is a alpha decay, right? Alpha decay. So it emits alpha and then breaks down to atom Y. Now, if you go and measure the mass, you go and measure the mass of before the breakdown. Okay, let's say you get something like 212.1 gram. And then you let it decay, right? After decay, you measure the mass again, you found that the daughter nuclei has a mass of 208 gram plus this alpha, let's just say is 4 gram. Okay, just an example, I just made up the values. All right, so after the decay, right, you total up the mass, you find that the mass is equals to 212.0 gram, and there is a drop in the mass compared to before the decay. Only a tiny drop. Okay, you see 212.1 drop to 212.0, so there's a 0.1 gram decrease in the mass after the decay. Okay, so what is this mass here? This decrease, this drop in mass, is what we call the mass defect. Okay, so mass defect is the missing in the mass. You find that some masses are missing. So where did it go? Where did the mass go? Here we found that in any radioactive material, radioactive reaction, the sum of mass before does not equal to the sum of mass after. Okay, unlike normal chemical reaction, they must obey the conservation of mass. So it's like whatever the mass before, you mixed it, after that you get the same mass. They obey the conservation of mass. Okay, but for radioactive or for nuclear reaction, any type of decay, we have alpha decay, beta decay, gamma decay, right? Any type of decay, you find that there's a mass defect. Okay, so what is happening here? Where did the mass go? The thing is, the mass, it is changed into nuclear energy. Okay, it is changed into what? It is changed into nuclear energy. Okay, now let me stress again. The mass defect happens when mass defect happens in nuclear reaction, and also any type of radioactive decay. Okay, it will occur. It occurs in any of these two. And where does the mass go is that the mass is actually converted. Okay, so we have mass defect, and then it is converted into nuclear energy in terms of thermal and plus kinetic. Okay, thermal and kinetic energy. Now, it turns out that it is these two energy, the thermal and the kinetic energy, that give the movement, that gives the motion to the alpha particle and to the daughter particle. Because when they break down, right, when they decay, the daughter particle and the alpha, they are being emitted at very high speed. Okay, they shoot out at very high speed. So that speed, who is giving them the speed? It comes from the mass defect. Okay, it comes from the missing in mass that has turned into the kinetic and the thermal energy. These two together, it is what we call the nuclear energy. Okay, so nuclear energy is just thermal and kinetic. It is from the radioactive decay or any type of nuclear reaction. Now, of course, it's mainly kinetic. Okay, it's mainly kinetic. This kinetic energy is used to make what? Alpha, make your beta, okay, make all these particles move. Okay, this is where they get their speed from. And not only alpha and beta, they also make the daughter atom, okay, the daughter nuclei move. It's from this kinetic energy. All right, so energy is mainly in the form of kinetic, okay, and also the fission fragments, any fragments that they get the energy from. Now, for the chemical reaction, for nuclear reactions, usually we don't use kg or we don't use gram. We use another unit we call the atomic mass unit. Okay, atomic mass unit, it is denoted as a lowercase u. Okay, so it is a constant of 1 u is equals to about 1.66 times 10 to the power negative 27 kg. Is very, very far. You see the factor is to negative 27. Okay, so that is 1 u. Or it can be thought as the mass of a proton. The mass of a proton is roughly estimate this mass. Okay, so that's 1 u, 1 atomic mass unit. It's a very small mass. Right, so now you get an idea of what is nuclear energy. So when the mass decreases, then the mass is converted into energy. And this energy is being released as speed and thermal. Right? So let's go to the nuclear fission process. Right? Let me go to the nuclear fission process. So we talk about nuclear reaction, right? There are two types. We have already talked about radioactive decay. There are 3 types of decay: alpha, beta, and gamma. So now we talk about what are the 2 types of nuclear reaction. We have, first is nuclear fission, and second is nuclear fusion. Okay, now we will look at it one by one. Let's start with the fission. Let me go to the next page. If you can take a screenshot if you want. I will go to the next slide. Right, look at this diagram. This is nuclear fission. Okay, do you need to memorize this? No need to memorize. They will give you one. This whole thing, no need to memorize one. Right. Here, N, okay, N is neutron, right? Neutron, and then we have uranium. They both decay, okay? They both react, nuclear reaction, and then they form barium and krypton, Kr, krypton. Okay, and also the neutron here. So what is happening here? Now, when you shoot a neutron, let's say you have a uranium atom here, right? You have 1 atom of uranium, and then you shoot the neutron to the uranium atom. The thing about neutron is that it has neutral charge, right? Neutral charge. So it can enter the nucleus of the atom. Because of the neutral charge, it will not be repelled. If you look at the nucleus is positive charge and the electron shell is negative charge, right? So only neutron can enter. If you remember, we discussed in the previous lesson, right? Only neutron can enter the nucleus because it will not be repelled. If it was proton, right, it will be repelled by the nucleus. If it was electron, then it will be repelled by the shell. So since it is neutron, then it can go straight into the nucleus. Now what happens is that when you bombard a neutron to the uranium nucleus, what happened to the uranium? Now the uranium nucleus has extra 1 neutron. And this extra 1 neutron will make the uranium become unbalanced, become unstable. Okay, so this become from stable, initially is fairly stable. Okay, become unstable because 1 neutron is added. And if you recall back, the stability of a nucleus depends on how many neutron and how many proton. Okay, if they're balanced, then it is stable. If you have more neutron, then it's unstable. So this uranium atom become unstable. What happened? It will decay, right? It will decay. So it breaks down and it forms two elements. They found that these two elements are the barium and the krypton. And also at the same time, another 3 neutron is given out. We have neutron number 1, neutron number 2, and neutron number 3. They are emitted also at high speed, right? So if you only focus on the first part of the reaction, this one, I shoot it, and then it breaks, and then it shoots out 3 more neutrons, right? What do I get out of this? If you go and measure the mass, okay, will there be a mass defect? Yes, there will be a mass defect, right? Whatever the mass initial, after breakdown, the mass, you find it. If you total the mass, it is actually slightly less than the actual mass, okay? So where does the mass go? The mass goes into nuclear energy, right? So it is why that all these neutrons, they move at high speed, they get the nuclear energy. So I can kind of add my nuclear reaction here. I plus nuclear energy. Okay, nuclear energy. Okay, now understand that it is not because of the shooting that breaks the uranium. Okay, it is because of the neutron go inside the nucleus, make the atom become unstable, then only it breaks. Okay, many people think that, okay, because I shoot it, it hits it, and then it breaks it. No, okay, it's not that. Okay, it's not what happened there. So it's first the neutron go in and then cause it to become unstable, then it breaks down. Okay, now and then when it breaks down, it sends out 3 other neutrons, right? These 3 other neutrons, they move at very high speed, and then they are going to target. They're going to target another uranium atom. You have millions and millions of uranium atoms in one single uranium rod. So these 3 neutrons, they will go and target another 3 atoms, right? Now the thing is, because these neutrons, they move at very high speed. Okay, they move at very high speed, right? Sometimes they will miss. Okay, sometimes they will miss the target, meaning that they just go and then they don't hit anything. Okay, or they just pass by an atom without hitting it. Okay, without bombarding with it. So what happened to that electron? The electron that missed, then it just die out somewhere. Okay, or it got absorbed by other material. Okay, so the thing is that these neutron does not hit any atom. Okay, so we have 2 left, right? 2 left. Now maybe the 2 hit another 2 uranium atom, right? And then it causes another breakdown, right? It hit another atom and then it got unstable again, and then it breaks down into the same fragments and release again 3 other neutrons. So this process repeat and repeat and repeat. This is the reaction we call nuclear fission. Okay, so how do you define what is nuclear fission? Nuclear fission is the breakdown of the parent nuclei due to the bombardment of neutrons. Okay, neutrons causing it to be unstable. Right, so that is nuclear fission. And in the process of nuclear fission, energy is released. Actually, a huge amount of energy is released. If you compare this amount of energy with normal energy that you get from chemical reaction, it is way above it. It's way more than chemical reactions. That's what makes nuclear fission become interesting. Okay, people want to do research on this one. Okay, because of the nuclear energy that they get out of it is it can make use. They can make use of that. Right. So this is an example of the chemical equations. Okay, they will always give chemical reaction here. Now, Just an example for extra, other than these equations, okay, we have like uranium, okay, uranium 235, 92 plus neutron, okay, plus neutron, meaning that it hit one neutron. Then you can also get alternatively, you get Xe, okay, xenon, and then you get Sr plus this 94 over 888, and then plus 2 neutron. Okay, what's the difference between these two? This one released 3 neutron, this one released 2 neutron. Okay, sometimes it released 3, sometimes it released 2, sometimes it released 1. Okay, and not all the time they will hit another atom. They might miss. They might miss. Okay. Now, here we will use the mass defect to calculate how much energy is produced by a nuclear fission. Okay, let me go to the PDF here just to show a bit of calculation using the mass defect. Okay, let me erase this first, and I go here. Okay, you should be seeing the example 3. Okay, so in a nuclear reaction, so it is talking about either the fission or the fusion. The mass difference mean the mass defect. Okay, in the reaction is 1.5 times 10 minus 3 kg. Find the heat released in this reaction. So find the heat released, that means find the nuclear energy. Okay, so what do we use here? We use equation, we use the very famous equation E equals to mc squared. This equation is founded by Albert Einstein, okay, through decades and decades of hard work. Okay, he came up with this very short and formula that explain everything, not everything, almost many of the stuff. Okay, it's E equals to mc squared. This formula simply tells you that whatever the mass defect, this is the mass defect. If you multiply by the speed of light, okay, speed of light in free space, speed of light in free space, that means 3 times 10 power of 8. Light travel different speed in glass, in water, but we want in air. So mass defect, you times by the speed of light, and you get the energy emitted. This is the energy. We call it the nuclear energy. Okay, so you can think of it like a torchlight, that if I shine the torchlight, open the torchlight, then it shoots out ray of light, right? It shoots out ray of light. Even in that scenario, in that situation, and there is a tiny mass defect. Okay, the mass defect is being converted into the energy, nuclear energy, and we can calculate that energy, okay, using this formula. All right, so if you apply in nuclear reaction, then we can take, right, E equals to mass, all these in SI unit, kg. So if it's given in atomic mass unit, you have to change it to kg. Okay, so E equals to 1.5 times 10 minus 8, and then we times into 3 times 10 power of 8 square. Don't forget to square. Equals to, okay, we calculate this and we get 1.35 times 10 power of 9 joule of energy. If you see this number, it's a very huge number. Times 10 power of 9, that's giga. Okay, 1.35 gigajoule. How much mass is the defect? You see the mass defect. Very small mass, 1.5 times 10 minus 8. That's like almost nano also, almost nano kg. So small the mass defect, but you get so large the energy. Okay, so that is the advantage of nuclear reaction. That's why people use it to make nuclear bomb. Okay, all the stuff, because you get huge energy coming out. Okay, so this energy, this amount of the energy release is about like 100 million times the energy released in an equivalent chemical reaction. And submarine, you know, submarine that they stay underwater for like months, okay, for about like 6 months. How are they able to stay that long underwater? Okay, where is their power source? Some submarine, they use what? They use nuclear fission. Okay, so they get their power source from nuclear fission. That is what makes them, okay, able to stay underwater for so long, okay, for a very long time, right? Okay, example 4. Another example, a nuclear explosion release this amount of energy. What is the mass defect of uranium-235 in this reaction? Okay, we use the same formula, E equals to mc square. Okay, equals mc squared. So 8.2 times 10 power of 13 equals to m, and then 3 times 10 power of 8 squared. All right, m equals to, we find that it becomes 9.11 times 10 minus 4. Again, very small mass, but very huge energy here. Yeah. Now back to the nuclear fission. Back to our slide. Right, you should be seeing my slide. Huh? Okay, so remember I said that when one nuclear fission, okay, take one breakdown as one nuclear fission process, okay, one process. So the 3 neutrons being released, they go and hit another one, and then they trigger another fission. Okay, they trigger another fission, and this one trigger another fission, trigger another fission. So you get something like a continuous reaction. This continuous reaction, what we term it as the chain reaction. What is a chain reaction? Okay, you see, a chain reaction happens when the 3 neutrons, at least one of them trigger another fission. And then you get another 3 come out, right? Coming out. And then that 3 also at least one trigger another one. Again, you get 3 come out and at least one trigger. So any one of the nuclear fusion, any one of the fission, at least one neutron is going to trigger another one. So that keeps the reaction going, right? Keeps the reaction going, that we call it as the chain reaction. Okay, so in chain reaction, you actually got 2 types of chain reaction. First is the control one. It is the control chain reaction. Control chain reaction. Another one is the uncontrolled. Control is like in every fission, in every breakdown, there is only one neutron trigger another one. Okay, so that is the control. For example, like this one, right? 3 come out, 1, 2, 3, maybe only 2 hit this one, and 2 come out, you have 1, 2, and also only 1 trigger. Okay, in every fission, there's only 1 neutron trigger another one. That is a stable control chain reaction. Okay, this is stable control. I can say that here, on average, there's only 1 neutron. 1 neutron induces another fission. Okay, induce means trigger, start another fission. On average, there's only just 1. That is controlled chain reaction. Now, on the other hand, we have uncontrolled chain reaction. Uncontrolled chain reaction is when you have too many neutron trigger fission, right? For example, the first fission, it gives up 3 neutrons, right? And then the 3 neutrons going to trigger another 3. So it's kind of like you get 1, and then you get 3 neutron, and each neutron trigger another one, right? So you get another 3 coming out from each of them. So you get what? 9, right? You get 9, and then the next one you get 27. 27, you get 81. By the 1, 2, 3, by the 4th stage, you already have 81 neutron. That is going to start another 81 fission. This is an example of uncontrolled. We don't want this to happen. This becomes a nuclear bomb. All right? So this is how nuclear bomb works. It works based on chain reaction. It is the chain reaction that causes this huge explosion, and a lot of energy is being released. Okay? So all they need is just one trigger. When the bomb hits, strikes one trigger, and it triggers the whole chain reaction. It becomes uncontrolled, and then boom, explode. Okay? So what we want here is the control chain reaction. Can we control it? Yes, we can control it. Later, I'll talk more about how do we control it. Okay? We can control this one. But there are many, many safety procedures, right? So one of the cases, the explosion of the power plant of the Chernobyl, right? So it's due to uncontrolled chain reaction. Okay, so it causes huge explosion. All right. Now, and also one more thing. One thing about the term critical mass. What is a critical mass? Sometimes you see this word. What is a critical mass? So if you remember, I said that the neutron is going to hit another uranium atom, right? And then start another fission. What about if there is not enough uranium atom? Okay, you have neutron, but you don't have enough uranium atom. What happens? Then there's no more fission. Then the chain reaction just stops there. Okay, suddenly stops. It breaks the chain, right? We don't want that to happen. Okay, we don't want that to happen. So you have to make sure you have enough of uranium atom ready for the neutron to hit, right? So how do you make sure that? That's why we have the term critical mass. Critical mass is the minimum mass. Okay, whoops. Minimum mass required to do what? To sustain a chain reaction. Okay, so it is the minimum mass required to sustain a chain reaction. The more mass, the more particle. Okay, less mass, less particle. So if you want to make sure there's enough particle for the neutron to hit, then there's a minimum requirement for the mass that you want to achieve. We call that mass critical mass. Okay, so if your mass, the fuel rod, we use uranium rod, like a cylindrical long rod. We put inside the reactor. The core of the reactor is uranium rod. Okay, we call it the fuel rod. It's the source of the radioactive, right? So this rod, it cannot be too small. Because it's too small, right? Too light, then it might fall below the critical mass. If it falls below the critical mass, then suddenly you get chain reaction, and then the chain reaction stops. And then you have to replace another rod. You have to do a lot of maintenance, all that. Okay, it's not practical. So you have to make sure that it is always above the critical mass, right? So that is the number one, the first thing that you need to take note. And also, all these fast-moving neutron, because most of the time they will miss the uranium. How do I improve the accuracy? They are very bad at accuracy. How do I increase the accuracy of the neutron hitting the uranium atom? I can increase by using graphite. Okay, graphite. I put the graphite around the uranium rod, like this, around it, just beside it like that. Okay, I put a graphite around it, and also sometimes they use water as well. You'll see that the fuel rod, usually they put it under water, right? In the nuclear reactor, they put it under water. So graphite and water, what they do is they slow down the neutron, slow down neutron, so that the neutron can hit the uranium atom, right? So if I use graphite and water, then I can increase the accuracy, and thus I don't need that high mass of the uranium because the accuracy increases. There are higher possibility for each neutron to hit the atom. So I don't need as much mass. So the critical mass can be lowered. Okay, does it make sense? Understand? The critical mass can be lowered if I slow down the nucleus because they have higher accuracy. Okay, they are able to easily start another fission. Okay, so understand that. And right, next one. Before we go to the nuclear fusion, okay, we talk about a few examples of calculation first. How to calculate the nuclear energy. Right. Let me go back to the document just now. Okay, example 5. Now, usually the exam type questions is like this. Okay, the exam type questions is like this. Calculate the energy released by the following uranium-235 nucleus. Okay, you are given an equation. That is the what reaction is that? That one is nuclear fusion, right? Okay, when you look at the product, uranium and neutron, so you know that is nuclear fission. Okay, nuclear fission, not fusion. Okay, here you are given the details: mass of neutron, atomic mass, okay, uranium, each mass, okay, the mass of each atom, and you want to calculate what is the energy release E by the entire nuclear reaction. Okay, so we apply the formula E equals to mc squared. E equals to mc squared. First thing, step number 1 is you want to find what is the mass defect. Okay, you want to find what is the mass defect. Okay, calculate the mass before and after, and then you minus to find the mass defect. Okay, so let's calculate the mass. Okay, we can calculate in U first. The mass of neutron, okay, before we get 1.008665 U plus the mass of uranium 235.043924 U. If you can, you take all the decimal. Okay, so 1.008665 24. Okay, we get 236.052589 U. Okay, so that's the mass before the reaction. After, then we calculate this one, CS, caesium 139.917277 U plus rubidium 92.033 U, and then plus this one, be careful, neutron, but we got 3 neutrons, so you need to times it. 3 times 1.008665 U. Okay, so we calculate this. The product, okay, we get the total is 235 865,305U. Okay, so after is always smaller than before. So mass defect, we minus it. This one minus this one, so I take mass defect equals to 235 minus 236 89U equals. Okay, so the difference is 0.187284 U. Okay, now this is the mass defect, huh? But this one is in atomic mass unit, so you want to convert it. You want to convert it to kg, so 0.187252 times 1.66 times 10 power negative 27. This is the mass of the proton. Okay, so equal to 3.109. This is negative 28 kg. This is the mass defect. Okay, so you get the mass defect from the equation, then you put in the equation 3.109 minus 28 times 3 times 10 power of 8 squared equals 2.80 times 10 minus 11 joule. This is your answer. Okay, so that is how you calculate the energy release. Sometimes they ask you the mass defect, sometimes they ask you the either the mass defect or the energy release. Okay, it's the same method. Now you see this one, why is it so small? 10 minus 11, because this is just for one atom. Okay, just for one fission. So in the real case, you have a lot of the fission process, a lot of multiple of this. Okay, a factor of this. Okay, next question. Question 6. Okay, what type of reaction is this? Okay, this is nuclear fusion. I will talk about nuclear fusion just after this. Okay, right after this. Okay, but the method is the same. Huh? Calculate the energy released in the following nuclear fusion. Right, so we have the mass, everything given. First, we find the mass defect. Okay, so same thing, mass before. We have 1.007825 plus equals to okay 3.021927 and mass after is 3. Okay, there's a mistake here. This one should be HE. So 3.3 3.016029 U. Okay. Mass of the helium. All right, so mass after minus mass before, we get the mass defect. That is the equals to 0.005898 U. I write change in mass, change in mass, and then we times by 1.66 minus 27. We get 9.791 times 10 power of negative 30 kg. Okay, so get the mass defect in kg, then we use E equals mc square times 3. Don't forget to square. A lot of students forgot to square this one. Then you get E is 8.81 times 10 minus 13 joule. Okay, next one. Finish. Example 7, okay, you try this. Do 7 and 8. Okay, it's a similar question. You do 7 and 8, and then you check your answer in the bracket here. Seven is what decay is that? This one is alpha decay, right? You see the nucleus of the helium 4,2. This is alpha decay. What about this one? This one, you see, plus E. This is beta decay. Okay, so alpha decay, beta decay, and the previous two we did, they are the fission and fusion. You need to be able to identify whether it's alpha decay or beta decay looking at the equation, because they'll always ask what type of decay is this, what type of reaction is this, especially in objective. Right, give you a few minutes to finish this two. You check the answer. If you don't get the answer, let me know. If you have problem solving it, let me know, and then we'll go to the next part. Okay, finished. Okay, we are going to have a short break. And after that, we'll continue to the next part. Okay, I'll give a 5-minute break. So we'll continue at 8 sharp. Okay, we'll come back at 8. Okay, guys, we continue. All right, next part. Now we finish with nuclear fission and we are at nuclear fusion. Okay, what's the difference? In nuclear fusion, we combine what? We combine deuterium and tritium. These are the isotopes of hydrogen. Okay, so deuterium is like H21 and tritium tri, right? Tri, so it has three 1. Okay, 3 nuclear numbers. Right, so these two molecules they are light molecules, they are very light molecules, and you combine them, right? Combine them, and then you get heavier molecules, helium. Okay, you get helium out of it. Now, at the same time, not only you get helium, you also get 1 neutron and also nuclear energy. Okay, so always there will be nuclear energy. Okay, now in the nuclear fusion process, what is the requirement for nuclear fusion process? The requirement is that it must be at very high temperature and also very high pressure. It is done at very high temperature and very high pressure. Why do we need high pressure? Because these two molecules, they are positively charged. So when you try to bring them together, when you try to fuse them, then it will repel each other. So how do you overcome this repulsion force? You have to bring it so close, right? So strong, hold it very strong, bring it very close until they fuse. So to overcome this repulsion, you need a very high pressure. Pressure is like compression. You imagine like you press them. Okay, you press and force them to get together, something like that. Okay, so very, very high pressure and also very, very high temperature. How high is the temperature? It's about 100 million degrees. That is very, very high temperature. Okay, so I write down here, pressure, very high, and also I need a very high temperature, about 100 million degrees Celsius. Okay, 2, the high temperature is used to break the bonds, and to overcome the repulsion easier. Okay, so because the two nuclei here, they are positively charged. So these are the requirements for nuclear fusion to happen. How do we make it happen? Can we make it happen? Okay, they are not still are not able to create this scalable nuclear fusion. It only possible in outer space, like the sun. Okay, inside the center of the sun is where nuclear fusion process occurs. Okay, so right now the sun is undergoing this nuclear fusion, right? Why it is able to undergo nuclear fusion? Because the sun is so massive, is so big, that the mass, the gravity is so strong that is equivalent to the high pressure that we need. And also at the same time, the sun is also very, very hot, right? So the gravity, okay, the pressure is from the gravity, and also plus the high temperature of the sun is able to sustain the nuclear fusion at its core, right? Not only the sun, other stars also do the same thing. Other stars, so our sun is just a small star, okay? It's considered like average size. In the outer space, there are huge stars, like the super huge one, like a million times of our sun. Our sun is already so huge compared to us, right? So those stars, they run by nuclear fusion. Is where they get the light energy from. Is where they get the heat from. Okay, it's how they survive. Is because of the nuclear fusion inside. Every single minute, it is creating energy from the nuclear fusion process. So that explains why the sun is so hot. Okay, so hot, so bright, is because huge amount of energy is being created from the nuclear fusion process. Okay, when the nuclear fusion, will it run out one day? One day the nuclear fusion will stop. Yes, one day the nuclear fusion will stop. When will it stop? When you have not enough of the hydrogen atom, the tritium, the deuterium. Okay, you have nothing left. Okay, you have no hydrogen atom left because you have already fused everything. You fuse everything, become helium already. Okay, you get helium gases. No more hydrogen. So what happened? Nothing to fuse. So the nuclear fusion will stop. And that is when the star starts to die. Okay, it is the beginning of the end. Right? So every star, they run by nuclear fusion. Now, if you compare the energy produced by nuclear fusion and nuclear fission, which one is more? The energy produced by nuclear fusion, right, is way more than the energy produced by nuclear fission. Okay, so from fusion, a lot more energy compared to fission. Okay, now the thing that is the good side of it. That's the good side of it. The drawbacks, the disadvantage of nuclear fusion is it is very hard to control. Okay, it's very hard to control, and also it's very hard to produce. That is why until today they're still not able to produce, to create nuclear fusion in the lab. Okay, so it is only possible in massive objects like the stars. Okay, now some bomb they use nuclear fusion also, like the hydrogen bomb. All right, some types of bomb they use nuclear fusion, but not at a very large scale. Okay, not scalable, we say. Okay, so that is for nuclear fusion. Okay. Okay, now next one, we look at the energy, the nuclear power plant. All right, the nuclear power plant. Now this one also they might come out in the exam, SPM, all that. Okay, they will ask you how it works, and what does this do, what does that do, like that. Okay, so this picture shows the power plant, the nuclear power plant. Basically, a power plant is something that generates electricity, right? But there must be a source. It generates electricity from what? From radioactive material. Okay, we said the nuclear power plant. So inside the core of the power plant is the reactor. This one you see in the picture. The reactor is the core. Okay, basically what is inside the reactor is it consists of the control rod, the graphite moderator, and also the uranium rod. Okay, all these three makes up the reactor. And it is placed inside a very, very thick concrete wall. Not the concrete wall in your house. It's a very thick one. Okay, very thick one. Why? Because they want to prevent all the radioactive to come out. Okay, so it cannot come out. It can block all alpha, beta, and even gamma. Okay, now how does it work? Okay, let's see. Inside the reactor, the uranium rod is the main thing. Okay, is the core, is the main thing of the whole thing here. It is the fuel rod. So what produces the nuclear fission? Okay, the nuclear fission. So here we are talking about nuclear fission, guys. Nuclear fission. Okay, this is a nuclear fission power plant. Oops. All right. So the fuel rod supply or sustain the chemical reaction, the nuclear reaction. Okay. So what does the graphite does? What does the graphite do here? The graphite, remember, I said that just now, the graphite is to slow down the neutron that is emitted so that they are able to hit the next uranium atom. Okay, the graphite is to slow down the neutron. Now, and then we have the control rod. What does the control rod do? The control rod is made of boron. Boron is like it is like a black powder, something like this. Okay, black powder. But here it is solid, right? At room temperature is solid. Boron, they use it to make the control rod. So why boron? Because boron is able to absorb neutron. Okay, boron, they can absorb neutron. Let me write it here. They can absorb neutron. Now, what does it do? When the reaction become uncontrollable, let's say sometimes you have many neutron that comes up. Okay, they have to monitor that. Okay, how many neutron come up? If they suddenly they got too many neutron, right, trigger the nuclear fission, then they have to cut down the neutron. How they cut down the neutron? They use the control rod. They will lower this control rod down. This control rod, they can adjust, they can raise it and then they can lower it. You can see in the picture is the blue thing here, the blue rod, this one. All this 1, 2, 3, 4, 5. Okay, they are the control rod. I can lower it. The uranium rod is the orange color. Okay, the orange color, and then place in between the black color, that is the graphite. Okay, so when I lower the control rod, okay, then it separates each uranium rod, right? All this, every single uranium rod is being isolated when I drop the control rod. Okay, so what it does is that if I drop the control rod, then all the neutron that is emitted, they will be absorbed by the control rod. Once they got absorbed by the control rod, then it's gone already. It cannot trigger another fission. Okay, so that is how they control the nuclear reaction, the nuclear fission. They cannot have too many neutrons come up because that would trigger, it will heat up the reactor. Sometimes the reactor will become overheat. Yes, you have to monitor from time to time. Also, if there are too less neutron being emitted, okay, they don't drop the control rod, they raise it up. Okay, they raise it up. So the control rod is only used when the reactor starts to heat up and when you have too many neutrons. Okay, and the graphite, remember the graphite is to slow down the neutron. These two, often they will ask you all the time, they will ask you what is the function of the control rod, what is the function of the graphite. Okay, one is to slow down, one is to stop, to absorb completely. Graphite is to slow down. Okay, so now in the reactor, they generate a lot of energy, right? They generate a lot of energy. So what is this energy used for? The whole purpose of the reactor is to generate energy, heat energy, and then the energy is used to boil the water. Boil the water in the heat exchanger, okay? Basically, you have water converted into steam in the heat exchanger. You can see the tube here, right? This tube, the heat energy is passed through the tube, right? And then you have water in the heat exchanger that is in contact with the tube. So it gets the energy, it got heated up, it changed into steam, hot steam that rush out. The steam rush out from the tube on top, and then it goes to the turbine. And what you learn in the electromagnetism, the turbine spin the generator, and then it induced electricity, right? Induced electricity, and then you get electricity coming up from here. Right? So these hot gases, hot steam, they are at very high pressure because it's hot, right? They rush and push the turbine to spin. Now, when they got into the condenser, and we use water to cool it down. Okay, cool it down, take the heat away from the hot steam, so they are allowed to condense. Okay, they release the heat and then they condense. Remember, when something condenses, you have like gas, liquid, and solid, right? Condensation is when you go from gas to liquid. It's condensation. And what happens in condensation? It releases heat. Okay, release heat. If you go liquid to gas, that's boiling or evaporation, right? That is absorb heat. Absorb heat. So if you go in reverse, that means it is releasing heat. So this steam, hot steam, release heat, and then it condenses back into liquid. and the liquid is being passed through the pump and repeat the whole process. So often you see this cooling tower, right? In the movies, in the TV, you see this very tall, very huge, like the shape of like a conical shape, the cooling tower. Okay, so that is for the heat to dissipate. Okay, at some time of the day, you will see that it releases hot steam. Okay, so it's for the heat to dissipate. Right, so basically that is how the nuclear power plant works. Okay, you have to know some of the components and to be able to describe it. Okay, now I have a few pictures just to show you what is inside the reactor. Okay, you may have seen, you may have noticed in the movies, right? Like this. Okay, this is a picture showing the control rod and a uranium fuel rod. Okay, you can see this one. The fuel, where is the fuel rod? The fuel rod is this one. Silver color, this one. Okay, silver color at the bottom here, this one, fuel rod. Oops, let me change color. Fuel rod. Okay, every single one of them. And then you have the control rod placed in between, right? In between of the fuel rods. So initially the control rod is like raised up. So if the reaction, you want to reduce the reaction, you want to slow down the reaction, and then you drop the control rod, okay, so that it starts to absorb all the neutrons. Okay, so you stretch it to all the way to the top here, this one. So from the surface, on top, you don't see this. This is what's inside the vessel. Okay, this is what's inside the vessel. From the top, you don't see what's inside here. You only see you only see the vessel, like cylindrical shaped vessel like this. Okay. And the next picture. Now this is what you see from the top. Okay, where is the reactor? The reactor is down there. And this one, you can see this one, all this. These are the reactors. Okay, and each of this is the vessel. Okay, the rod. No, sorry, not the vessel, it's the rod. All right, so you can see the whole thing, and this one is being submerged underwater. This is water, all these are water, it's underwater. Okay, the uranium rod and the control rod, they are all submerged underwater. Why? The water is actually used to cool it. All right, to cool it is because water is a very good insulator. Okay, very good insulator. So it is used to cool down the rod. Okay, when the reaction takes place. And also, if you remember, water is also used to slow down the neutron, right? Water and graphite. It can slow down the neutron. So you see, often they submerge the rod underwater. Okay, it's submerged underwater very deep inside here. So this is basically the core of the reactor lah. Okay, is the water dangerous? The water, does it contain radioactivity? Because it's submerging the uranium, right? Is it dangerous? Can you jump in? If you accidentally fall in the water, what happened to you? Actually, the water it contains a little bit amount of radioactive materials, but if you happen to accidentally fall inside, nothing will happen actually. Okay, it's not dangerous. It's not dangerous. You can even swim in it. You can even swim in the water here, but you don't go too near to the reactor down there. If you go too near to the reactor down there, then you'll be exposed to the radioactive. Okay, you cannot touch all this rock. But if you swim like on top, okay, there's no harm. Okay, you can do that. Okay, there's no harm. Right? It's perfectly safe, even if you fall into the water. Right? Okay, what else? Let me see. Okay, I think that basically sums up everything. The nuclear energy and also the mass defect. And also we looked at the two types of nuclear reactions. Okay, the nuclear